Hello, my name is Cameron Amati, and I'm a PhD student working towards a PhD in environmental science with a focus in toxicology. I'm in Dr. Ed Mager's lab. We've done some work in the past with lead, and we did co-exposure to hypoxia, and we were exposing Daphnia magna looking at different toxic effects. So for the purposes of my presentation, I thought it'd be fitting to discuss lead as the toxin. As mentioned, I'll be discussing lead. So first, let's look at some of the background information on lead. As you can see, this is lead here on the periodic table. It has an atomic number of 82 and is a post-transitional metal. Lead is a ubiquitous non-essential metal, meaning it has no biological function but is very common in the environment. Its non-essential description is characterized by this graph that we see, which is similar to ones that we've seen before in the semester. It shows that at low concentrations, there is a toxic effect but with some tolerance. As the concentration increases along the x-axis, we see a continual decrease in the physiological health with no sort of hermetic curve that we would see with something like zinc. Although it's not needed biologically, the chemical and physical characteristics of lead provides many practical functions in things like industry. Of the uses of lead, the main use of lead is in lead-acid batteries, which accounts for about 85% of the total global consumption of lead, and its predominance is still growing. Uh, Even though that's the main use of lead, the largest source of environmental lead pollution is through mining and smelting processes. Many regulations have been put in place in the US to help mitigate the effects of these occurring, but in predominantly developing countries, it's still a large issue and unfortunately affects children disproportionately. Other sources of lead of toxicological concern are from lead bullet waste and lead fishing weights. Bullets and weights might off first impression seem negligible compared to batteries, but can be a significant environmental concern depending on the location and hydrogeologic setting. As mentioned, lead is naturally occurring in the sediments, crust, and water on Earth, and is naturally released through weathering and volcanic activity. However, anthropogenic sources of lead are a much larger contribution to the lead that we see in the environment. The effects of lead toxicity have been documented dating back thousands of years, with evidence of its use shown to have affected the Romans and Egyptians, who used lead for things like water pipes, as pigments and paints, and even as an artificial sweetener for consumption. Historically, the most evident impact of lead toxicity were the neurological and behavioral effects. However, these effects are still relevant today. The reason why lead has the symbol Pb is for the word that's really fun to say that is plumbum, which is Latin for waterworks. In more modern times, lead has been used in things like even still in plumbing, pigments, cosmetics, as well as an anti-knocking agent in gasoline, which is a pretty famous use of lead, which led to very high levels of atmospheric lead pollution. What we see here in this graph is the usage of lead in different sort of capacities. So over the course of decades on the x-axis, we can see that that blue portion of the graph is the use in lead acid batteries, and that portion is increasing in its fractional use over the course of many decades to be the most predominant use of lead. The route of exposure for lead can vary from inhalation, ingestion, dermal absorption, absorption from retained or embedded leaded foreign body, or transplacental routes. Inhalation and ingestion are the predominant forms. Inhalation typically occurs from lead being used in something like paint or uh, sort of old materials. So people get exposed when they do projects like DIY at home, renovations, and they're not wearing the proper safety protocols and safety equipment that help clear uh, any sort of particleized lead in the air. Ingestion occurs through paint consumption. So this is a most predominant for children. Children will consume paint from the wall or play with toys that are coated in leaded paint. Dermal absorption can occur, but this is at a much lower rate historically since the banning of leaded gasoline. Absorption from retained or embedded leaded foreign bodies. What this is saying is it's if you swallow something like a lead ball, for example, you're going to have some of that lead leach into your body. And then there's transplacental routes. When lead is used in these industrial processes, in things like lead acid batteries that leach lead into aquatic ecosystems, it will often find its way into water where it can expose aquatic organisms like fish to toxic levels. One important thing to consider, though, about when talking about the toxicity of lead is its bioavailability, which is defined as the portion of a drug or substance which enters the circulation when introduced into the body and is so is able to have an active effect. The bioavailability can change depending on certain things like water chemistry and different water parameters like pH, alkalinity, natural organic matter, and other parameters. When these change, the bioavailability of lead can also change, making it less toxic. So we can see on this table by Turner et al. That the major lead species, when in more acidic environments, tends to be the free ion, which is one of the most bioavailable forms. So in aquatic ecosystems around neutral pH, lead is not complex and is not as bioavailable. Also, lead salts are more available under acidic conditions, making it more toxic. The general effects of lead toxicity can be broken into two categories depending on the molecular target of lead. So, one, it can be proteins that bind to zinc, or two, proteins that bind to calcium. So, these two are largely affected by uh, lead, and that's because they're all cationic divalent metals. Zinc and calcium, however, are biologically needed for regular function, while lead is not. And so lead kind of hijacks these natural pathways to gain entry into the body, which leads to these competitive interactions. So, one of the effects that we see from lead toxicity is calcium antagonism. So, this leads to hypocalcemia and leads to bioaccumulation in calcified tissues, so things like bones and teeth. What's not as clear is if lead is a biomagnifying toxin. One of the reasons, a hypothesis for this is that if lead is stored in things like bones, how much of that is going to be transferred through trophic level when consumed from a lower trophic, when consuming a lower trophic level. It might not be a great source of transfer. Other toxic effects of lead are neurotoxicity and behavioral effects, and anemia. So, lead can cause reactive oxygen species mediated hemolysis, as well as microcytic and hypochromic red blood cells. And specifically, lead can disrupt ALAD. So, ALAD stands for aminoleuvolinic acid dehydratase, and it's something that we'll talk about going forward further because it's been important for my research and what we're working on in our lab. With regards to the interaction of lead and calcium, the main cause of acute toxicity is ionoregulatory dysfunction. So, calcium uptake can be inhibited due to this competitive interaction we talked about previously with lead, which can result in hypocalcemia and low calcium levels in the plasma. The transport pathways that appear to be most at risk for the uptake of lead are the calcium pathways. For fish, for example, the transport of calcium occurs via the chloride cells located on the gills. Um, this sort of competitive interaction in fish gills can be modeled by tools that aquatic toxicologists have created called the biotic ligand model, which takes into consideration the bioavailability components that we've talked about previously that kind of modulate how toxic the lead is. Um, so lead accumulation also occurs in the posterior region of the kidney. Lead disrupts the reabsorption of calcium in the proximal tubule and results in excretion of calcium, which significantly contributes to hypocalcemia. Lead is a well-known neurotoxin as well. So in mammals, it will disrupt the peripheral and central nervous system, and during development, lead affects differentiation, leading to dysfunctional alterations in circuitry. So this is a large concern for children who, uh, in previous decades, were in America were at risk for lead exposure from consuming things like paint chips or putting toys in their mouth that were painted with lead-based pigments. This isn't so much a concern now because different litigation and regulatory processes have been put in place to protect children, but in developing countries, children are still at a very high risk in certain regions. So less research has been done in other biological systems, looking at neurotoxicity, so things like fish, but also other taxes. So the effects of lead as a neurotoxin isn't as well known. One of the last effects I'll be discussing about lead toxicity is its effect on zinc-containing proteins. So ALAD, which we mentioned before, which stands for delta aminoleuvolinic acid dehydratase, is an enzyme that catalyzes an important step in the heme synthesis pathway. So it's a pathway that forms hemoglobin. So ALAD contains a unique catalytic zinc binding region with three cysteine residues. So at this region, it has been shown that lead can bind 500 times more strongly than zinc. And this disruption will block or disable the ability for hemoglobin to be synthesized, which can lead to anemia. Anemia is a condition where you lack enough healthy red blood cells to carry adequate oxygen to your body tissues. So there can be a few different manifestations of this. So there's microcytic anemias where the red blood cell are smaller than normal, or hypochromic anemias where the red blood cell has less hemoglobin than normal. And so this is largely attributed to the inhibition of ALAD that we previously spoke about. I wanted to touch on briefly some of the work that we've worked on in our lab, that being Dr. Ed Mager's lab. In case there's any students out there that are interested in working in sort of aquatic toxicology or metal toxicology in a similar format that we've been testing these organisms in. So the test organism we're working with is Daphne magna, so commonly known as like a water flea. So in the middle picture, you can see two different daphnids. The one on the left is slightly darker, and so that's the presence of higher levels of hemoglobin in the organism than the one on the right. So in our lab, we were experimenting exposing daphnids to two different variables. So we were exposing them to lead, which has been shown to cause variable effects on hemoglobin, such as the decrease of ALAD activity. And so because of that, hemoglobin synthesis won't be able to occur as well. The second part of our co-exposure was hypoxia. So we put them in a chamber, we flush the chamber with nitrogen and lower the percent oxygen. And so when these organisms are exposed to hypoxia, it increases their ventilation and heart rates. They also increase their hemoglobin concentration, and they also can change their hemoglobin binding affinity by switching to a different isoform of hemoglobin, of which they have 7 different forms. So there's a little bit of a conflict here. So hypoxia is, as a result of hypoxic exposure, the daphnids naturally want to increase their hemoglobin concentration, but lead is going to inhibit that. So that was the focus of the research project that we were looking at, and we plan on continuing this research, looking at different things like epigenetics and gene expression of the different isoforms. In modern times, many regulations and laws have been put in place to protect and limit the risk of lead toxicity to humans as well as to the environment. Two organizations that do this are the United States Environmental Protection Agency and OSHA, the Occupational Safety and Health Administration, as well as others. But these are two predominant ones. Uh, the EPA has put in place different acts like the Toxic Substance Control Act, the Clean Water Act, the Safe Drinking Water Act, and the Clean Air Act, which all aim to limit and control lead toxicity or the lead exposure, lead pollution, and different things like that. OSHA has set the permissible exposure limit, the PEL, of lead to be no greater than 50 micrograms per cubic meter averaged over an 8-hour period. For general industry, a time-weighted average cannot exceed over 30 micrograms per cubic meter. Lead has an LD50 for the mean body weight of a male of around 4,665 milligrams per kilogram, and for females, about 5,610 milligrams per kilogram. It has been reported that the lethal oral dose of lead acetate for humans is about 714 uh, milligrams per kilogram. There are still many ongoing issues with lead toxicity today. Perhaps the most prevalent is the Flint water crisis. Overall, regulations have served well to protect the majority of people that perhaps in the past would have been at a greater risk for lead exposure. For example, the Clean Air Act, which was administered by the EPA, is held as one of the greatest successes when it comes to environmental litigation. Thank you guys for watching my presentation. My email's here in case you have any questions about the lead toxicity that we discussed or the research that we're doing if you're interested in partaking in something like that in the future. I appreciate it. Thank you.